Now in section 2.3, you're going to actually learn 8 different objectives, but they're all highly correlated and synced together. So the main gist of it is this: you're going to find the equation of a regression line and then use it to make predictions. We're going to figure out, determine the linear correlation on the calculator. We're also going to estimate the linear correlation by just looking at a graph. You're going to explain what the correlation coefficient means in a real-life context. And then you're going to understand when the correlation and the sum of the squared residuals are better for determining if a model is good. 14 here, find the line of best fit algebraically. This is something you need to know how to do for the test. Interpret the slope means in the real-life context, and then also compute a line center of gravity. Again, a lot of objectives, but they flow together just so nicely that it's almost like doing one big problem, and we accomplish all of these at the same time. So let's do them. Now in the notes for 2.2, we learned how to write the line of best fit by hand using y equals mx plus b. Today's lesson is really going to focus on using the calculator. So the portions of the calculator that I need to show you in class, I will revisit after we do the entrance card. Let's just start with this. Linear regression. What that is finding the line of best fit using your calculator, not doing it by hand. That's what regression means, is do a calculator regression. So what it is, it's the method for finding the line of best fit, and it was first published by the French mathematician, I believe it's Adrien Legendre, back in 1805. So I thought this was interesting because it just shows you this mathematical method has been around for hundreds of years. All right, the line of best fit is known as the least squares regression, or the regression line. So the least squares line or the regression line. And again, we use our calculator to do it. The 3 important properties is what it does is this. First, it minimizes the sum of the squared residuals. The second thing is it contains what's called the center of mass. And the center of mass is actually a very easy calculation. What you do is if you have all of your ordered pairs in your data set, you just take the mean or the average of the x's and then the mean or the average of the y's. That ordered pair is actually the center of mass. And you can kind of think of it in terms of a teeter-totter. It's like the center point that allows a thing to be level at a certain point. And then the third important property is that the slope and the y-intercept can be computed directly from the coordinates of the given data points. Now, referring back to the data in section 2.2 on the diamond, we have the carat weight and the price. That's our x value and our y value, our independent and dependent variables. They want us this time to use a statistics utility, that basically means a calculator, to find the line of best fit. And what I'm going to do is in class, I will show you how to do this, but basically you're going to end up going to, if you want to jot some notes down for A, you're going to go to Stat, Edit, and you're going to enter the data into list 1 and then into list 2, and it's going to be in ordered pairs. So this will all be in the first ordered pair, the second ordered pair, and so forth. And then after we do that, we just do Stat, and we go to Calc, and you're going to find the lin regress. And that is going to give you the output from the calculator. So if you want to try that now, you can. It's actually not that difficult, but we are using primarily the Stat button every time. So let me show you though, when you do this on the calculator, what you're going to get back for the equation is this. It's going to tell you that the slope of this data is 5501.53, and that's x, so that's the m. The b, or the y-intercept, is 372.67. Okay. Now we can actually go to part B for this. It says, according to the regression line, how much will a 0.5 carat diamond ring cost? Well, all you need to do is realize that the 0.5 is the weight, that's the x value. Just put that value in for x and simplify and see what you get. When you put 0.5 in for x, what you're going to get for part B is the answer is going to come out to be $2,378.10. So you may want to double check that you get that in your own calculator. Now, part C says verify the center of mass is actually on the line. The center of mass, what they did, by the way, again, is they took all the x values and they found the average. They took all the y's and they found the average and they got the center of mass. To verify it's on the line, it's very easy to do. Again, this is the x value, this is the y value. What you want to do is just substitute that in. So put this value in for y, and then put the x value in. Then we'd subtract the y-intercept. And what you should notice is when you do this, that this calculation on this side, when you simplify, has to equal this amount. If they equal, that mathematically confirms that the center of mass sits on the line. Okay, part D. Find the sum of the squared residuals for the linear regression. Okay, in part D, this is something that we can use the calculator to help us to do. And we did talk about how to find the sum of the squared residuals in section 2.2. Let me just revisit for you what it is. You're going to find the sum, so sigma, of the squared residuals. Well, a residual, remember, is observed minus predicted. And it's the sum of those squared. So what you technically need to do is to realize up here in our data set, this is the observed value. We need to come up with the predicted. Well, I will show you in class how our calculator can get us the predicted values. All the predicted value is, for example, if I were to take 0.15 for a caret, put that back into the equation, and you're going to get a value. This is going to be your predicted. Okay, you can do that for everyone. I'd put the 0.12 in for x and get what the y is and put that value right here. That's predicted. So then all you need to do is take the observed minus the predicted and get an answer over here. Take that answer and square it and then add those all up. Again, this is one thing I'll show you in class how to do on the calculator. Okay, this next example says, use the least squares regression line to estimate the price of a diamond ring weighing 0.17 carats. Again, the hardest part is just realizing if that's the x or the y. Keep in mind for our equation, x was the weight, so all we need to do is take x out, and we're going to put in here the 0.17. Check your computation carefully. You should get that the predicted price is $562.59. So what you want to take away from this, by the way, though, that's what the regression line gives you, is the predicted amount. Now, the next thing I want to talk about is correlation. When you do a linear regression in your calculator, the calculator will give you the equation answer. In addition to that, they're going to give you, in that equation, a letter R. The letter R is the linear correlation. And what you're going to find is this. This is the calculation for it, by the way. Okay? It's quite intense. You are not going to have to do this by hand. But let me break it down for you for a second. What it says is take the sum, right? We're going to take every single x that we have, subtract the mean, and divide by the standard deviation. And then times that by every single y, subtract its mean, divide by its standard deviation for every single ordered pair. Do that for every ordered pair, add those up, and then come in and multiply by 1 over how many are in the data set. And that'll give you this correlation coefficient. Again, the calculator is going to do all that work for us. Here's the important thing about it. This number is always between -1 and 1. And what it does is it indicates two things. It indicates the direction of the relationship and the magnitude, or a word you might be more familiar with, the strength. Okay. So does the direction, is it a positive sloping direction or is it a negative sloping? And how strong is it? Okay. If R is positive, we are said to have a positive relation. And that says that data moves in the same direction. Well, what that means is if you look at a graph, for example, a line with a positive relation means as x goes up, y goes up. So as this x goes up, that y goes up. So what you're going to see is a positive sloping line. So a positive sloping line will end up having a positive correlation. Now a negative correlation is a negative relation. And how that works is this. The data moves in the opposite direction. So in this case, they're saying, as for example, if our x gets bigger, the y's will actually get smaller. So if we draw that relationship, what you're going to end up seeing is maybe something along these lines. Okay, the lines will go down. Again, as x gets bigger over here, notice the y corresponding to that is negative. All right, if r is 1 or negative 1 exactly, it is said to have a perfect linear relationship. Thus, it has perfect correlation. And when it has perfect correlation, it's going to intersect and hit every single dot in the scatter plot. Okay, a strong correlation means that most of the data is close to the line. A weak correlation means a linear trend may be seen, but the points are not very close to the line. Okay, and I'm going to show on the next slide what the pictures would look like for these correlations to have it make more sense. So let's do that. This is a great slide in that they want you to kind of estimate what we think the correlation is going to be. If you look at graph A, you're going to notice that as the x values go up, so do the y values go up. So that means this is a positive correlation. So I know it's positive. And if I were to come in and draw a line of best fit, it would be this one right here. You're going to notice it's going to hit every single data point. This correlation is probably a +1. Okay? On the flip side, the graph right below it, this says that as the x's get bigger, you're going to notice the y values get smaller. So here's the x was up here, there's the y. When the x is up here, the y goes down. So this is a negative correlation. And this, if I draw a line of best fit, will end up hitting all of the dots too. Therefore, this is a perfect negative correlation of -1. All right, graph B, hopefully you can tell it probably has a positive correlation. Okay, E here looks like it has a negative correlation. And if you had to estimate, I would say graph E, the dots are a little bit closer to the line, so it's going to be negative. However, it's going to be somewhat strong, maybe a 0.7, and I don't know exactly. Graph B, it's a positive correlation. These dots are spread out a little bit more than the bottom graph, so I'm going to say it's not quite as strong of a magnitude, maybe a 0.6. Okay, so the plus or minus tells me only the direction. The absolute value of the number itself tells me how strong it is. Now, graph C and F, if we do a linear correlation, you know, maybe for C I would draw a line here, maybe I would draw the line there, maybe I draw it here. It's really somewhat unclear. This has very bad linear correlation. If it has very poor linear correlation, it's going to be very close to 0. And that's what I'm going to say that one is. Now, letter F you have to be careful about. It looks like it may have a possible linear correlation. It looks like that you could possibly draw a line here, or we could draw a line here. The problem is it only represents half of the graph. So technically this graph has very poor linear correlation, and this one is going to be very close to 0. What this has is more of a quadratic formula related to it, and that's what we would get into later on in the chapter. You know, take 10 seconds and look at this scatter plot, and I want you to decide between these 5 multiple choice options, which one do you think is the best answer in terms of what the correlation would be for this graph? Pause the video, check it out. Okay, in pausing it, hopefully you realize it has to be a negative correlation, so it's A, C, or B, and it's a pretty good line. So I would say the best answer is going to be a -0.9. We could draw a line of best fit. You know, it may only hit a few of the dots on the scatter plot. That's fine. But you're going to notice how tight that line is with the scatter plot itself. I just want to briefly highlight this activity. This is something what they'd want you to do is to draw a scatter plot. And I would use your calculator because you're probably going to have to do this in homework. For example, for set 1, put this in list 1. And put this in list 2. And then you're going to want to go and do a scatter plot for that. And if you have questions on how to do a scatter plot in class, I will go over that. The thing to keep in mind to do a scatter plot, you're going to hit the button on your calculator, do second stat plot, or which is the y equals button. And in there, you're going to choose to do a scatter plot. You are going to have to put the data in the calculator. Again, to put this data in the calculator, you're going to go to the stat button and edit, and just enter in list 1 and list 2. And then again, this is where you're actually going to graph it. And what they want you to do is just look at the pattern of the graph and determine the correlation. So I'll leave that to you to do for extra practice. Now we only have 2 slides left. This question here says, if r squared is 0.6, what are the possible values for r to the nearest 10th? Now, for our purposes, we don't really talk about r squared in regression analysis. It does have a meaning, but we don't need to go there. But we know r has a meaning. That's a correlation coefficient. It tells us, again, the direction and the magnitude of the strength of the linear relationship. Well, if r squared is equal to 0.6, how do you find r? Don't overcomplicate it. To get r by itself, you take the square root of both sides. So when you do that, you're going to get that r is approximately, to the nearest 10th, is going to be 0.08. Okay, that's a pretty good correlation. But I have to tell you, this is not the only answer. A 0.08 correlation is positive, so it means odds are our scatter plot looks something like this in a positive direction. However, keep this in mind. If I put 0.8 back into here, again, this is approximately. If you do 0.8 and you square it, you're going to get approximately 0.6. But there's also another number I can put in here, just not 0.8. I can put negative 0.8 in there. So you have to be very careful. There's 2 possible answers here. The correlation coefficient is either plus or minus 0.8. I don't know. I would have to look at the data set. If it were minus 0.8, it would just be a downward sloping data set. Now, the last thing I need to caution you about with correlation is this. Correlation does not imply causation. You have to use logic to determine if you think it really, the nice correlation caused it. Let me give you an example. What if I surveyed everyone in class and I said, you know what, I want to know, gather some data about how many cupcakes you had this week, and then your average hours of sleep per day. Okay, your hours of sleep. And let's say I did a scatter plot and I just noticed that as the number of cupcakes went up that you consumed, that those folks ended up having more sleep. So I ended up getting this nice linear looking relationship. And it came out with maybe a correlation coefficient of approximately 0.9, which is a very strong correlation coefficient. Does that correlation coefficient tell me that the amount of cupcakes that you eat per week is going to impact your sleep? Did it really cause it to happen? This is where they say use logic. You know, odds are no, so you have to be very conscious in how you interpret the data set. Okay. The second thing to be very cautious about with correlation is that outliers in your data have a very strong impact on the slope and the y-intercept and the correlation. So let's say this is the blue data is my graph on your cupcakes and sleep, but then I had someone else who was way over here. Okay, that would be an outlier. If I do a linear regression on this data set, it is going to have an incredibly large impact and skew my slope, my y-intercept, and my correlation. So definitely look at the scatter plots first to see if you have any real obvious looking outliers in your data set. Okay, that's it for section 2.3. Again, if you make the entrance card when you come to class, this will be modified. Otherwise, this will be your assignment. Let me know what questions you have. And if I don't cover enough on the graphing calculator in class, folks, let me know because I want to make sure you're comfortable with how to do that. Thanks.